We'll move on now to the second part of Module 6, which is set theory. This is very similar to what we did in the previous submodule on mathematical logic, and also has some connections to probability theory. For those of you with a serious interest in mathematics, set theory is quite related to probability theory, and this was established essentially in the second half of the 19th century. So I'll mark also connected to probability theory. And I've already mentioned Cantor and for his contributions to set theory and probability theory and, of course, mathematical logic, and it won't be the last time I mention him. So the idea of set theory is to give a formalization to the notion of I have a collection of elements. I want to understand what types of things are in here and develop a notation for that, and how do different sets interact at the level of do they have elements in common? Do they have no elements in common? What happens if I combine the elements in the two sets? What happens if I take only the elements that are common to both of them? Set theory is the descriptive language for this. So let's look at some notation. So an element X is said to be in a set A, and we write X is contained in E or is in A. Sorry, contained in A. So this E here, or this E-looking thing, is really an epsilon, Greek letter. So we denote that the point of object X is not in the set A by writing the same thing but with a line through it to say it is not in the set. We give a name for the element of the collection of all things not in the set, which is the complement, AC. Sets have an interesting notion of containment. If I have two different sets, it's possible that everything in the one set is also contained in the other set. This gets a special name. This is called being a subset. So the definition is here. If every element of a set B is also in the set A, we say that B is a subset of A, denoted B contained in A. So this is somewhat different than the notion that X is an element of a set. This is saying that I'm making a comparison between two sets. If everything in B is also in A, then we say that B is a subset of A. There is a rather trivial case of subsets, which is when A and B are the same set. If this is not true, if actually they are different, but B is completely contained in A, we say that B is a proper subset of A. We can define notions of algebra that perhaps are familiar by now. We've seen these for probability theory. We've also seen them for mathematical logic. These are just notions of or and, notions of intersection and union. So as for probability theory, we see the union of A and B is the set of things in either A or B. So it grows the two sets. It puts them together. The intersection of A and B, denoted A upside down U, A, B, is the set of things in A and B. So it's restrictive. You need to be in both A and B to be in the intersection. The difference of the set A from B is the set of points that are in A but not in B. So take everything that's in B and remove it from A. Whatever's left is the difference. And then we give a special name to the set that has nothing in it, the set of no elements. We call it the empty set. This models in some way the notion of zero for addition. It's the thing that does nothing. If I union with the empty set, I add nothing, so I stay the same. So A union the empty set is always equal to A. Conversely, if I take an intersection with the empty set, I get the empty set back. Because nothing is contained in the empty set, and the intersection has to be contained in both A and the empty set. Okay, so a nice picture that I drew in the earlier modules for probability theory is the notion of a Venn diagram for sets. Okay, so the union I'll shade in purple. And the intersection I'll shade in green. So just a nice warm-up example here. I'll take as my first set the collection of points 1, 4, 6, and 7. And as my second set, the collection of points -1, 3, 6, 7, and 8. Let's compute the union and the intersection. The union is the things that are in either of them. So A union B will be -1, 1, 3, 4. I don't count 6 twice. I count it just once. And I also count 7 just once. So that's the union. And then the intersection are the things that are in common to both. So what's in both? Well, the number 6 is in both, and the number 7 is in both. And that's it. This is just a warm-up example for us. In the next submodule, we'll look at a much more involved example where we look at complements as well as intersections and unions.